In this video, we're going to learn about differentials. First thing, what is a differential? Well, a differential is an infinitesimal value, oftentimes looking at something like dy, dx, df, etc. And it can usually be found, by treating the derivative, which is a limit of difference quotient, as a fraction. So let's see some examples of how this works. First example, given f of x equals secant of x squared, find dx. So the first thing I'll do is take df dx. I'll need to use chain rule, so that's going to be secant x squared tangent x squared times 2x. And I need to solve for this dx. So the first problem is it is in the denominator. I'm going to multiply it by both sides to get it to the numerator. So df equals, I'll bring the 2x to the front, 2x secant x squared tangent x squared dx. And then I'll divide both sides by 2x secant x squared tangent x squared. So dx will equal df over 2x secant x squared tangent x squared. Now that's a way to find differentials. Going back one step, what's a use for them? Well, we can oftentimes, when we're doing df, it's going to be equal to f prime of x times dx. This is an exact equality, but I can use it to approximate actual changes. Delta f will be approximately f prime of x times delta x. In a linear sense, this would be the same delta f and delta x that you would find if you had done a linear approximation. So let's see some applications of this in tolerance problems, knowing how accurately I can measure something, seeing how accurately I can calculate something. So you know that you can cut the side length of a square to within 1 millimeter of its actual value. How close can you get the area of the square to 49 square centimeters if you're attempting to cut a 7 by 7 centimeter square? So first off, the idea here is I'm going to say, okay, we're dealing with the area of a square, so area equals s squared. And they're telling me that I'm within 1 millimeter, so that's 0.1 centimeters. Let me write down 1 millimeter equals 0.1 centimeters. So what they've told me is this, and this is the important thing to see. If I can measure the side length within 1 millimeter, that means that ds, the magnitude of ds, will be less than or equal to 0.1 centimeters. Now again, it is an approximate because this is not linear, and ds changing into delta s comes from a linear approximation, but it'll give us a very good approximation very easily. And for the next example, it's really the only good option I can think of off the top of my head. So what I'm going to do is, this tells me about ds, how far off the side length is. I want to find dA, how far off the area is, so I'm going to use a related rate here and say, okay, dA ds equals 2s. I'm going to solve this for ds, so dA equals 2s ds. Divide both sides by 2s, so dA over 2s equals ds. And now, this is where the magic happens, I can replace this ds with this value because it equals ds, and I see that, okay, dA over 2s is less than or equal to 0.1. I have absolute values, but that doesn't matter for this 2s. 2 is positive. The side length of a square will always be positive, so I can multiply both sides by 2s and get the magnitude of dA is less than or equal to 0.2s. And I can bring this out of the absolute value, but I can't bring dA out. dA could be too big, so being positive, or if the area is too small, dA would be negative. So I can't bring that out. But what I can do is this. I'm shooting for a 7 centimeter side, so that means that dA will be less than or equal to 0.2 times 7, or dA is less than to 1.4. And in written English, what this means is the following. If I can cut the length of the side of the square within 1 millimeter of its actual value in this case, then I can get the area within 1.4, and I'm dealing in centimeters here, squared centimeters of 49 square centimeters. So this is how far off my area could possibly be. Before I go on to the next example, just a little side note. So this is an approximation. Basically, you have two cases. Worst case on each end is being 1 millimeter too short on both sides, so 6.9 by 6.9, or 1 millimeter too large on both sides, 7.1 by 7.1. This one here, I think is going to end up being 1.39 centimeters too small when I multiply through and get the area. This one's going to be 1.41 square centimeters too big. So you can see this is a very good approximation for what we're looking at here. All right, final example. And this is one where I can't necessarily just plug in some values because I don't actually have the size that I'm looking for. I just know how accurately I can measure it. So you want to measure the surface area of the Earth to within 5% of its actual value. How accurately will you need to measure its radius to achieve this? So I want to measure the surface area, so how far off the area is to within 5% of its actual value. So that's 5% of the area. I go through the same process. So the formula we have is A equals 4 pi r squared, and take the derivative, dA ds equals 8 pi r, and I want to solve for dA here to replace this out, so dA equals 8 pi r ds, sorry, dA dr, 8 pi r dr, don't know where that s came in, I do know it was the last problem, but okay, so now that I have dA, the magic can happen where I can take this 8 pi r dr and replace this dA with it. So 8 pi r dr has a magnitude less than or equal to 0.05. And if I leave this as A, I'm going to try to move this 8 pi r over. A and 8 pi r are different terms. One's based on the other, but they're different terms. So instead of having this A here, I'm going to bring in what A equals, which is 4 pi r squared. That way, when I move this away, things will cancel for me. So I'm going to divide by 8 pi r. Actually, let me multiply this through first. So the magnitude of 8 pi r dr is less than or equal to 4 times 0.05 is 0.2. I have a pi r squared. I'm going to divide both sides by 8 pi r to try to get dr by itself. Just like before, that's possible even with the absolute values because 8's always positive, pi is always positive, and the radius of a sphere will always be positive. These all cancel, so I'm left with the magnitude of dr is less than or equal to On this side, pi's cancel. One of the r's cancels. And I have 0.2 over 8. Now, 0.2 over 8 is the same as 0.1 over 4, which is going to be 1 over 40 r. And I can also do this, so 1 over 40, so dr is equal to 0.025 r. And this tells me in English the following. We need to measure the radius r within 2.5% of its actual value. I hope this helped out. Feel free to comment below if you have any questions, and I'll get back to this after winter break.